Hello, ladies and gentlemen. Today we want to examine the effectivity of a ferrite rod, the dependency on shape, frequency, screen, coil position and so on. The first test is about the DCF signal to transfer time data from an atomic clock to watches everywhere here in Western Europe. A tuned resonant circuit consisting of a coil on a ferrite rod and a parallel capacitor offers measurable signals, shown by the red pitaya, a small modern oscilloscope with web-based applications. As you can see, there is an obvious peak at a frequency of 77.5 kHz, and it depends on the ideal direction. In time of 1 second the magnitude varies, and the duty cycle of each low and high magnitude defines a high or a low of a bit. So let's start with a simulation. After we start, we have to make some settings. At first, a file name is requested. And the problem type is AC magnetics. And it's axisymmetric. The unit is millimeters. And the accuracy is high. The geometry consists of the outer boundaries and the ferrite rod and the coil themselves. First, the outer boundaries. Second, the ferrite rod. And then one winding in the center of the rod. By the way, the x-axis is the center of the rotation symmetry. We define some materials now. This very small point is the first central winding. And the material is copper. And the outside room, it's air. And this is the ferrite rod itself. Now we have to add some windings. We want to add 24 windings on the right side and the same on the left side. So in the summary we have 49 windings. Now, very important is to define the material's properties. The permeability of air is 1 and there is no conductivity in air, so it's set to 0. Next one is copper. We assume the conductivity of copper is about 60 million Siemens per meter. And we let flow a certain current to be able to examine the magnetic field coming from the rod. The ferrite's relative permeability can be about 200. This is a usual value for the rods for radio frequency purposes. After the mesh command, the whole arrangement is being solved and the results can be seen. By the way, you can see the segmented areas, more or less fine dissolved, easily spoken dependent on how strong the changes are which are in focus. And we should adapt the picture's properties. This means we want to see the magnetic flux density. Now we want to adapt the color scale and define this as a status, so that we can use these properties for every solved state. We can measure the impedances. Especially the most interesting thing is the inductance of the coil on the rod. Next step is to increase the frequency 1,000-fold. After solving, we can use the picture properties we defined before by selecting the appropriate file. As expected, the inductance is 1,000-fold as before. We want to see the changes when we will shift the coil across the rod. What do we expect? Yes, we can think that the inductance decreases. And indeed, the starting value with the centered coil is 258 microhenries. Then it decreases to 159 microhenries with a border position coil. And now we go back to the centered coil again. Let's have a look at the H field strength as well, because we want to see the influences of a conductive foil in the near of the ferrite rod. The foil is being constructed. The foil's material properties have to be defined. Just 1000 Siemens per meter is a very low conductivity in comparison to 60 million Siemens per meter of copper. You can see the influence to the H field is only very weak. What happens if the foil conductivity is increased to 100,000 Siemens per meter? You can see the shape of the H field is very distorted now. Now we will use a foil of copper with a conductivity of 60 million Siemens per meter. The situation now. Almost nothing of the H field can leave the inside room. Of course, consider that we look at the direction from rod to outside. In fact, we want to see the direction vice versa in order to examine the reception properties with and without a screening foil. We will make the foil thinner now. and the foil goes closer to the coil. For now, conductivity is 10 Siemens per meter. We change the frequency again. And now a circuit is added as we want to control loads later on. First of all, the coil is shorted, as we want to examine the short circuit current. The foil is shorted as well. The front end wall is now an emitter of a magnetic field. And this edge label has to be defined with special properties. And the whole model has to be remeshed. Now the inner currents are on focus. For the coil current, it's necessary to mark just one winding. The short circuit current in the coil becomes about 1.9 milliamps, while the current in the foil is about 0.4 milliamps. Now we increase the foil's conductivity to 1000 Siemens per meter. The short circuit in the coil is nearly the same. The foil's current goes up to about 40 milliamps. Further increase of the foil's conductivity to 100,000 Siemens per meter. The coil's current decreases to 0.54 milliamps. The foil's current increases to 180 milliamps. We remove the short circuits now and measure the voltages across the coil and foil. As you can see, the foil's voltage is lower by the factor of the ratio of the windings between coil and foil. We want to examine the E-field effects, so we have to switch the model from AC magnetics to AC conduction. The front wall gets a voltage potential against the foil, which is conductive too. The foil needs an edge label too, and the potential has to be 0. Between the ferrite rod and the foil there is almost nothing left of the E-field, which dominates outside. Now let's have a look at the course of the E-field strength. It is illustrated by the diagram. Now the model shall be transferred to plane parallel. We get something like a cage with an emitting front wall. Its name is rotation emitter, and the other three walls are set to 0 of magnetic potential. The materials have to be defined too. We measure the magnetic flux density in the rod depending on different directions. Now we want to make the magnetic field coming from the side. The value of B is much less if the direction is lateral. That means the magnetic wall is on the side. We go back to the axisymmetric model again. Our intention now is to survey the influence of the rod's geometry to the electrical results. For this, the rod is divided by a line horizontally. And vertically. Every section still consists of ferrite at the moment. And this state will be measured initially. Now the rod is half of the length. And we will make it hollow now. And full length again. Each geometric state of the rod is measured. These are the results of varying rod length and cross-section. We are finished now. Let's have a look at the summary of the final results. Ladies and gentlemen, thank you for your attention.